Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 51 today and we are discussing about bending of thin sheets. This is what we started discussing in the last lecture and we are going to continue doing it today. So, we have derived the expression for elastic energy, which is basically the bending energy of the thin sheet, and we have defined that what is this flexural rigidity, that D is equal to E h cube by 12 1 minus sigma square. We have derived this. Now, let us say that at this state the bending is increased by an infinitesimal amount, that is delta amount. So, therefore, the elastic energy of this film or this thin sheet, that increases by delta FPL. So, amount, this much amount of energy it increases because infinitesimal increase in bending of this thin sheet, because of which this delta increases by delta zeta amount. So, therefore, this we can write it as E h cube by 24 into 1 minus sigma square and delta of del square zeta by del x square whole square dx dy, and so this is equal to let us say this is E h cube, this is 24 into 24 1 minus sigma square into delta of this is delta goes inside now, let us say, and here it will be 2, this will be 2, this is del square zeta by del x square into this will be del square delta zeta by del x square dx dy, because the incremental energy that is required to increase the extent of deflection from zeta to zeta plus d delta. So, so it is like this. So, this delta FL F can be given as this quantity. Now, this has to be integrated. So, remember that this is uniform about the y axis. So, I can just simply write it as, let us say, E h cube by, let us say that 2 goes out. So, it is 12 1 minus sigma square into, let us say this is width is w, let us say, and therefore, it is integration, this is del square zeta by del x square into this is del square del x square and this is delta zeta and let us say dx, it is like this. So, it is like that. Now, we have to integrate, we have to do this integration. Let us say it is I, and that is equal to, this is integration of del square zeta by del x square, and here it is del square delta zeta by del x square into dx. So, this can be written as so this can be written as this is let us say I have to integrate it. So, I will write it here like this, yes, del square zeta by del x square, and here it will be del of zeta by del x minus. So, I will derive this quantity over here. So, it will be del cube zeta by del x cube into this will be del of zeta by del of x. Remember, here it will be integrated, we have to find out between minus L by 2 to plus L by 2, and here it is dx. So, I am just integrating it by parts, and so here it is further can be written as del square zeta by del x square into del of zeta by del x. This is minus L by 2 to plus L by 2, and it is minus here. So, here it will be, let us say, minus. So, again del cube zeta by del x cube into del of this will come out, right. So, it will be delta of del zeta minus, here it will be, you have to derive this quantity. So, it will be, sorry, it is not square, this is cube here, it is also cube here, not square, this is cube here. So, it will be del 4 zeta by del x 4, del 4 zeta by del x 4 into it will be zeta del x, del zeta, yeah, del zeta, it will be del zeta here. So, we start with here del square zeta by del x square. So, it is integrated over here. So, this quantity comes out to be del zeta by del x. So, here del zeta, so it becomes del zeta by del x. So, this quantity is fine. Now, over here this is minus L by 2 to plus L by 2. So, we have integrated it. So, it is del zeta here. So, it will be del zeta here. Now, to integrate it like this. So, it is derivative quantity here. This is fine. So, it is like that. So, here what we can see is that this part and this part. So, it can be shown that this part will be equal to 0, okay, because this is being integrated over the whole range. Actually, if you see the book, it has been further derived these quantities and these quantities to say that the integration is being done over a closed loop or like that. So, therefore, these quantities and this quantity, this del here, this quantity and this quantity will be actually equal to 0 over this limits from the whole range minus L by 2 to plus L by 2 or like that. So, what will be left with is this quantity. So, therefore, here we will be left with delta F is equal to, so here it will be, we will be left with here only this quantity. So, del 4 zeta by del x 4 and delta zeta dx dy like that. Now, dy of course, I did it in a little differently over here. So, let me write it over here and here it is d, because I am writing it d actually to make my life easy. So, it is like that. So, this is the bending energy that is stored in this plate. So, the bending energy of course is this. Now, we further integrated. In essence, what we have done is that we have found out that if we increase the deflection by delta zeta amount. So, it increases from zeta to zeta plus d zeta. So, there will be an infinitesimal increase in the bending energy. So, that is this quantity that we have found out. Now, that has been done, this increasing deflection, that has been done by an external load. So, this external load which acts perpendicular to the plate, let us say that is P. So, the energy, P is here. So, the energy of this load, okay, energy of this external load, external force, let us say, okay. So, that will be given as what? Minus P into delta zeta, and this has to be integrated over the whole area. So, it is dx dy and the same way that you have done it over here like this. So, the total energy will be minimum and that will be equal to 0, and that will be obtained by adding the energies, this delta infinitesimal change in the energy of this plate and also the external force. So, that means delta F plate and then here it is minus P and this is delta zeta here and dx dy integrated, this is equal to 0 and this one is equal to, we have just obtained, this is equal to d into d4 zeta by dx4 into delta zeta into dx into dy, we just obtained it. Okay. So, that is this part, that is this part. So, therefore, okay, we have in essence integration sign d, this is d4 zeta by dx4 minus p and this is delta zeta dx dy, this is equal to 0. So, this is the thing that equilibrium, okay, the energy will be minimum and therefore, this quantity right hand side, okay, that has to be equal to 0. So, if the right hand side is equal to 0 and this is the integration over the whole area, okay. So, therefore, this integrand at every point has to be equal to 0. So, what it means is that d4 zeta by dx4, okay, is equal to P. That is the balance of force. So, this is the bending force and this is P is the external load that is applied on this plate. That is all it means. Of course, there are boundary conditions that will come and I will describe in a minute, but here it is the condition for minimum energy of the system consisting of the plate and the external load will be equal to this, and therefore, we have obtained that this d into d4 zeta by dx4 minus P equal to 0. So, that is the balance of force. Now, this analysis can be extended to bending about both x and y axis, because here only when you have only bending about y axis, okay, for that we derived d, and this is del d4 zeta by dx4 minus P is equal to 0. So, it is about both x and y axis. Let us say both x and y axis let us say. So, this force balance equation will be then d and delta 4 zeta minus P equal to 0, and this quantity is what? This is del square by del x square zeta plus del square plus del y square, del square zeta by del y square. This delta is equal to delta operator, this delta operator is equal to, so this is this, so delta operator is like this. So, del square by del x square plus del square plus del y square, so that is all it is. So, this is the way it is, and if it is not rectangular, let us say cylindrical quantity or polar coordinate or cylindrical coordinate, let us say it is like this, then we will have this term will be equal to del square by del r square plus 1 by r del by del r, okay. That is the way it will be there. So, suppose a circular disc, okay, has been applied some load, circular disc, right, and it is being bent. So, there is a theta symmetry though. So, in presence of theta symmetry, right. So, this is let us say r capital R, or let us say small r is r, and it is being bent because of application of load, let us say because of gravity only it bends like this. Then the bending, okay, will be equation that you have to solve or worry about, okay, will be this quantity where this delta operator is like this, like that. Now, of course, the boundary conditions have to be defined. Now, so remember that this is a fourth order differential equation. So, there are 4 boundary conditions required here. So, we have to define that. So, let us say we come back to this xy coordinate, and let us say the plane is freely supported at the edge x is equal to L. So, plane is freely supported at the edge x is equal to L. So, let us say it is something like this. This is the plate, and let us say that here it is freely supported. So, now freely supported means that this support is only applying the vertical resistance here, a vertical load here, okay. There is no torque applied, there is no torque applied over here when that is freely supported. If it is clamped over here, then both vertical load and the torque gets applied. So, the torque, remember the torque is given as d into del square zeta by del x square, curvature. So, the torque is given by flexural rigidity into curvature. So, when torque is equal to 0, what it means is that the curvature, okay, this is the curvature, that also equal to 0, del square zeta by del x square is equal to 0. So, when I say that the plate is freely supported at the edge at x at any edge or at x is equal to L, let us say. So, what it means is that at x is equal to L, the curvature is equal to 0, and if we, and the boundary condition can be 2. In one case, boundary condition can be what is this load that is applied, that may be one boundary condition, and the other boundary condition can be that what is this deflection, okay, at this point, that can be another boundary condition. So, when we say that the plate is freely supported at the edge, then both these things can mean. One is that if we know that what is the delta here, that is the displacement, vertical displacement of the neutral axis, that we know, or let us say we do not know that, but we know what is the load being applied, that is F or R or whatever. Okay. So, it is like that. So, both of these, either of these things are known. So, that is all it means. Now, when force is known, when the F is known, then F will be defined like this. Okay. We can actually derive this quantity, this expression, but you just take it for the time being. F is equal to minus of d and del cube zeta by del x cube at x is equal to L. So, you have the expression for zeta as a function of x. So, you find out the triple derivative at x is equal to L, where it is freely supported. Okay. So, this is, so either this or this is given and this quantity is also given. That is all it means when we say that the plane is freely supported at the edge. Now, if the plate is clamped at the edge, then what it means is that, let us say this is rigid wall and let us say that the plate is clamped like that. So, what it means is that there is no deflection over here. So, therefore, this zeta over here, okay, at x is equal to L, it is x is equal to L, let us say. So, this is equal to 0. Okay. And secondly, the neutral axis, okay, the slope of the neutral axis at this point also will be equal to 0, because it is clamped like that. So, therefore, del zeta by del x at x is equal to L, that is also equal to 0. So, we need 4 boundary conditions. So, 2 at one end. So, these are given by this for general problems. There may be some different here and there, we can discuss about that, but there are 2 different kinds of boundary conditions. In essence, what we want to say is that one case plate can be clamped, and for that we have these 2 boundary conditions. Another can be the plate can be freely supported, for which there is no torque. So, the curvature is equal to 0, because there is no torque. Curvature, the torque is 0 means curvature 0, and then either zeta or F is defined, and if zeta is defined, it is fine. If F is defined, means F is basically given by this equation. So, you have to equate F is equal to this quantity which is there in the right hand side. So, it is like that. Now, let us solve a problem, and that will explain our these concepts. A beam of length L0 5 centimeter, width 5 millimeter, thickness 150 micron is clamped to a rigid wall at its one end. So, that means it is clamped here, rigid wall, while its other end is subjected to a vertical load 5 grams. Consider the Young's modulus and the Poisson ratio of the beam are this, considering that weight of the beam contributes significantly. So, if there is no load, the beam will be straight like this, but there is a load there. So, a load being applied over here. So, therefore, beam has got some amount of bending over here, that is all it means. So, some amount of bending there. So, the load has been applied. So, let this load has been applied is P. So, P is 5 grams. So, let me convert it into Newton. So, it is 5 into 10 to the power minus 3 kg into 10, this is Newton. So, this means it is 0.05 Newton. That is the load that has been applied. So, remember this load is what this F mean over here. It is freely supported, means there is no load is being applied, essentially freely supported, and over here, okay, at this end, this zeta is equal to 0 and del zeta by del x, this is equal to 0 at x is equal to 0, let us say. So, it is like this. Now, this kind of loading is called the concentrated loading. So, here the concentrated load is being applied at the length L. So, let us say that because of this bending there is no increase in extension, okay, of this rod. So, the beam length remains constant at L0 is equal to 5 centimeter. So, that has to be assumed. Its width is 5 millimeter. So, actually what we need to obtain here, okay, we can obtain it like let us say F will be equal to P by W. So, it is 0.05 Newton, and this is 5 into 10 to the power minus 3 meter. So, this is here I will write, this is equal to 10 to the power minus 3, right. This is 0.05, 10 to the minus 2 here. So, it is 10 Newton per meter. So, this is the load that has been applied. So, load means per meter width, right, like that. Now, what is the flexural rigidity, that also I can calculate, because E and H are given. So, D is equal to E into H cube by 12 into 1 minus sigma square. So, this is equal to E is how much, 50 gigapascal, 50 into 10 to the power minus 9 pascal, and thickness is 150 meter micron, 10 to the power minus 6, this is cube, by 12 into 1 minus 0.48, this is square. So, you find out what will be this value. So, this is in Newton meter. So, you can estimate it. This comes out to be 0.0183 Newton meter. So, let us say it is 0.0183 Newton meter, and here F 10 Newton per meter, that I have already obtained. So, now we need to solve this equation. Remember that vertical deflection of the beam, okay, can be obtained by solving the following boundary force balance equation. So, which means that if it is bending is only about y axis, this is this equation. So, remember that the P is equal to 0 here, because there is no load that is applying within this region. Within this region there is no distributed load. So, the P is basically distributed load, right. So, because that is the way we derived it also. So, there is no load over here. So, therefore, this P is equal to 0. I hope you appreciate this, that in this case the load is concentrated being applied over here. There is no distributed load from x equal to 0 to L0 over here. So, therefore, this P is actually equal to P is equal to 0 here. So, therefore, we have this equation. So, what is the solution of this equation? Solution of this equation will be equal to zeta is equal to, so it will be, let us say C0, let me use the same expression over here, plus C1x plus C2 x square plus C3 x cube. So, we need to estimate this C01, C2, C0, C1, C2 and C3, we need to estimate that, and that is what we will do by using this boundary condition, which I have already described to you, that these are the boundary conditions. So, at x is equal to 0, zeta is equal to 0, what it means is that C0 will be equal to 0. So, this will be equal to 0 here, and let us say del z by del x also equal to 0. So, that means C1 also will be equal to 0 here. I am doing it little fast. So, del z by del x if you write, okay, then C1 will be there at x is equal to 0. So, that is equal to 0. So, C0 and C1 is 0. So, we are left with two other constants we need to solve, and that we will do by from these boundary conditions. So, del square zeta by del x square, let me do it here only, del square zeta by del x square is equal to, this is 6 C3 x plus 2 C2, right, because I am finding. Now, this is at x is equal to L0 is equal to 0 here, and so therefore, this C3 is equal to minus 2 by 6 is 1 by 3, and this is C2 by L0. So, it is C3 is equal to minus 1 by 3, because it is 2 is equal to, so 2 by 6 is minus 1 by 3, and C2 and L0. So, it is like this. So, C3 is equal to this, and then the other condition is this. So, this also we have to find out. So, del cube zeta by del x cube. So, that will be equal to del cube zeta by del x cube. So, that is equal to, from here it comes out to be 6 C3, and so this is minus d. So, let me go to this. So, it is equal to minus d, and it was 6 C3, 6 into C3, okay. This is equal to f here. So, here this gives C3 is equal to minus of f by 6 capital D, so flexural rigidity, right, and d square by dx square. So, that has given us C3 is equal to minus 1 by 3 C2 by L0. So, here C3 is equal to minus 1 by 3 C2 by L0, right, that is what we got here. So, here C2 will be equal to minus 3 L0 into C3. So, C3 is minus minus plus, this is f by 6d. So, this is equal to f L0 by 2d, like that. So, we have obtained both this C2 and C3, and the other quantities also we have obtained, right. So, therefore, this zeta, okay, will come out to be, this is minus f by say C3 into x cube plus f L0 by 2d. So, that is into x square, we just derived it, right. So, that is all, that is the profile, okay, or bending profile of this particular plate, which is being clamped at one end, and the other end there is a load that has been applied. So, I want to ask you that what is the kind of dependence of this deflection, okay, with respect to x. So, you know that this is not a simple expression, I mean it is a cubic equation with respect to zeta. So, that is the interesting thing about it. And yeah, so now what it says in this problem, let us see, considering that the weight of the beam contributes insignificantly to its bending, obtain the vertical deflection of the beam at its middle point along the length at x is equal to 2.5 centimeter. So, here what I need to do is, I need to find out at x is equal to 2.5 centimeter and given all these expressions. So, here let us say, therefore, zeta will be equal to minus, now F is 10 Newton per meter, I have already obtained, and D is 0.018, I guess 0.0183 Newton meter. So, here it is 0.0183 Newton meter, right, and this is x cube. So, x cube is L0 by 2 whole cube, right, L0 by 2 whole cube, and then the plus, this is 10 here and this is 2 here, 0.0183 into this is L0 here, and then x square is L0 by 2 whole square, right, and L0 is equal to 2.5 centimeter 10 to the power minus 2 meter. So, you substitute all that, okay, and you can obtain what will be this quantity zeta at x is equal to L0 by 2, x is equal to L0 and all that, and this is not difficult. So, find out, it will come out, you can obtain this whole expression, this comes out to be 7.18 millimeter, that is the answer for it. Then the next question is that obtain the bending energy of the beam, and that I have already done because these expressions are already there. So, this is integrated over y means it is uniform, so that it is just width that you have to multiply. So, the total energy that will be d, it is d by 2, I have already told that it will be d by 2 into curvature square. So, the bending energy I have already derived d by 2 into curvature square, and you integrate because that is per unit area. So, integrate over width, we integrate over x, and so here we need to do it that with respect to x, that is all. So, here with respect to integrate with respect to x we need to do. So, del square z by del x square, okay, comes out to be this expression from here. So, therefore, we substitute over here. So, this is f square by 2d, this is del square z by del x square whole square, remember that. So, we have to find out f4 by 2d whole square, and you do all that. So, this is not x square, this is del square z by del x square, right, at del x square. So, it is f into f by d, f by minus f by d into x minus L0. So, it is f by d, so it is d by 2 here, so it is square of that. So ठीक है. So, this is f square by 2d x minus L0 square, this is fine. So, you substitute all that and finally, you get this expression for integration from 0 to L0. So, this is the total bending energy of the beam. So, and then of course, you can put the numbers and you can find it out, okay. And so, it will come out to be like this with these quantities that is already there. So, please substitute and see if this value that I have estimated is correct or not. I hope you appreciate this particular part. So, here actually I should have written it minus f by d into x minus L0. So, you are finding a square of that. So, it is f square by d square, but is d by 2 is there. So, therefore, f square by 2d into x minus L0 square. So, that I hope you can easily understand. And then you substitute over here for this quantity, and then you can obtain further. Now, there is only, so it is d by 2 already have multiplied, that is why it is here. Okay. So, this is fine. So, that is all for today. and we will take up some addition problem in the next lecture on this. Thank you for your kind attention.